Hello. Can you hear me? It's noisy. Okay. Noisy, too loud. Can you adjust the volume? Hello? Okay. Okay. I guess it's okay. Come on.
Petróleo. Bom, hoje, então, nós vamos receber, tá, a professora Whitney, tá, da Purdue University, lá dos Estados Unidos. Eu vou fazer, então, uma introdução e agora a gente vai fazer a transição para o inglês. Apenas um ponto, né, a ser levantado. Nós vamos ter uma apresentação de uns 45 minutos, né, 50 minutos. Após essa apresentação, nós vamos ter espaço para perguntas, tá? Essas perguntas são muito encorajadas, tá? Né? Tanto pela professora Whitney, quanto por nós, tá? A gente quer saber dúvidas, né? Qualquer dúvida. Por favor, faça alguma pergunta, tá? Essa pergunta pode ser feita, né, em português, em inglês, acho que espanhol dá também, tá? Mas, por favor, né, façam alguma pergunta no final, então, da nossa apresentação, tá? Eu vou fazer, então, a introdução da professora Whitney, tá? Ok? Professor Whitney is here with us today. So she is a professor of mechanical engineering at Purdue University in Indianapolis and an adjunct research professor of Vascular at Indiana University School of Medicine, Indiana, USA. She has been recently awarded as Fulbright U.S. Scholar to Brazil, collaborating with me here at Udesc for developing digital technologies for oil recovery and sustainability. Professor Huidan has been recognized as leader to image-based computational fluid dynamics for translational, biomedical, and energy applications. Holding dual Ph.D. degrees in physics and engineering, she brings extensive research expertise with over 100 publications, 3 U.S. patents, more than 100 invited and contributed talks. Professor Yu has been at the forefront of developing GPU-accelerated ICFD and digital twin technologies that integrate advanced physics-based modeling with real-world clinical and engineering challenges. Her interdisciplinary work has advanced innovations in patient-specific hemodynamic assessment, vascular graft design, and subsea oil spill mitigation. A dedicated local, national, and international collaborator, Professor Yu engages across academia, healthcare, and industry to deliver impactful, computation-driven solutions. So, let's welcome Professor Yu.
Thank you. Bom dia. Tudo bem? Tudo bem. That's what I can say right now. Hopefully I still remember after the talk I will see Charles, but not right now. Okay, that's something I can say right now. So it's my honor actually to present my research in kind of a broader audiences in Udesc. This is my second visit. Actually, last year I visited, the Geoenergia Lab. Professor Hegele's lab last year, 2 weeks. I actually did a lot of talks, but within the group. So this time to kind of a broader audiences is my honor. So today I am going to talk about something very new in the research, even worldwide. It's called digital twin technologies. Okay, so very brief introduction. introduction about myself. So I'm a professor in mechanical engineering in Purdue University, but actually my undergraduate was physics. And I actually did 2 PhDs in physics in China, Peking University, and the second one was in aerospace engineering in Texas A&M, USA. After that, then I did 2 postdocs in Johns Hopkins and the Los Alamos National Lab. Then after that, I actually joined previously Indiana University, Purdue University in Indianapolis. It's IUPUI. Now it's Purdue University. So that's kind of pretty much my background. The reason I am introducing this, I want to show you some research scientist like me, without any medicine or biology background, but we can make big contribution to healthcare. Okay, I can do it. You can do it. Okay. Okay, so talk about the U.S. Brazil collaboration. So Luiz just mentioned that I recently got this Fulbright to Brazil. It's actually a big honor because highly competitive. So based on the previous collaboration with the Luiz group, so basically next year I will come 3 months through that program. Okay, so more. So I'm showing actually pictures. So these are in the U.S. We met. I mean, Brazil colleagues in the U.S. This is the last APSDF meeting. And because last year I visited here already, so we had a lot of fun time. And I think many of you are in the pictures, you recognize yourself, okay? So in terms of the research, the collaboration, basically my group is developing digital twin technologies. Like today, I will mainly talk about the medical application. But meanwhile, I want to develop these digital twin technologies for petroleum engineering applications. So which is the subsea spill mechanical dispersion on that part. So hopefully I can make contribution to the petroleum engineering kind of the research area besides the medical, because my own research more focusing on the medical side, okay? Then we're doing collaborative mentorship of like undergraduate students, graduate students to uncover like new fabulous physics. So basically through high fidelity computation modeling or simulation, hopefully we can unveil those new fabulous physics which may previously not found because of the computation limit. Okay, and also we're developing joint research proposals, and we are doing faculty and student exchanges between U.S. and Brazil. So it's a very meaningful project. Okay, today I am going to talk about first is the image-based GPU-accelerated CFD, which is within my expertise. And also I will introduce the very new kind of topic. The term is called the digital twin. Okay, and then I will present 2 digital twins with kind of 2 applications. But mainly I will talk about this one because the healthcare digital twin is more mature. Okay, and the digital twin for that SMD is still under construction. So I will only talk about the idea. So hopefully next year when I visit, then I will present that with the like results. Okay, and then I'll have some take-home messages for you. So what is CFD? I think from majority students in Luiz lab, so you all know what CFD is. But to the general audiences, I would say computational fluid dynamics is to use numerical methods and algorithms to simulate and analyzing fluid dynamics, especially for these kind of real systems. For example, this is the large simulation in this turbine, I mean the engine computation. This is the blood flow in human arteries. You see a lot of red blood cells, right? This is the blood injection in the left ventricle in human heart. Okay, so people are doing this kind of CFD, simulating that kind of flow systems. And this one is kind of a very funny phenomena about a droplet, how it bump up and detach, then drop, then reattach. A lot of physics there behind. And this is the kind of well-known what we call vortex street. It is kind of when flow pass a cylinder or a sphere, then it will develop a very rich physics behind the object. Yeah, so, oops. Okay, yeah. So again, a lot of physics there. So people are using CFD to unveil new physics, finding kind of new insights from these kind of simulation outcomes. Okay, so in terms of fluid dynamics, actually there are 3 levels to describe the fluid dynamics. What we are very familiar with is on that macroscopic level. It's kind of the river, the lake, like the water, wherever you can see, right? There is kind of the flow there. Actually, if you have higher than high school education, you know each substance, each matter is made of numerous particles, right? Molecules. Although we cannot see them, but if you have a very advanced kind of the microscope, you can see them, right? But if not, you can also imagine, okay? So we can describe fluid dynamics. I'm going to skip all those kind of terminologies in fluid dynamics. This one and this one is what we know, we accept. But actually in between, there is a scale, it's called the mesoscopic level, which is a bridge to connect the macroscopic level fluid dynamics to the molecular motion. Okay, so in that case, we can have an advantage if we describe the fluid dynamics on this mesoscopic level. We can take care of both sides. Okay, because on the macroscopic level, you never see the air inside, you never see the molecules, right? And you even do not imagine when the air is made of molecules, right? But on that level, actually, it's very hard to study. Even you want to do CFD, it's very limited because of the numerous particles. You know, one mole takes 10 to the 23rd particles, right? So if you do simulation on that level, it's called the molecular dynamics. It's very, very time consuming. So in most cases, for real application, it's not capable to do that. So between these, so basically, that is the research expertise I have, and also Luiz, his group. So it's called Boltzmann equation. I mean, the number equation is the Boltzmann equation. So yeah, so in terms of this computational methodology, if we use the Knudsen number to characterize the flow regimes, so Knudsen number connects the hydrodynamic, the macroscopic level scale, to the molecular motion, which is called mean free path. Okay, so this ratio is Knudsen number. Knudsen number in general, it can vary from 0 to infinity. Okay, so this is the direction it can increase in. So in terms of Knudsen number, actually there are kind of 4 flow regimes. And a continuum flow, basically with the Knudsen number smaller than 0.01, that is something, I mean, the flow regime you can solve using macroscopic level CFD, okay? But if moving toward to that direction, actually, you can see with some kind of boundary treatment, you can still use Navier-Stokes. Navier-Stokes sequencing is for the macroscope level, right? So you can still do CFD for that. But beyond that, then Navier-Stokes equations are basically not valid. So you cannot solve Navier-Stokes equation to kind of study the physics for those flows. Okay. So in that case, in general, numerical CFD method based on Navier-Stokes equation has the limitation in application, whereas for numerical method based on Boltzmann equation on the mesoscopic level, it has a broader application. Okay, it's more fundamental in general. So that is kind of the motivation to develop mesoscopic level lattice Boltzmann method to do CFD. Okay. So now let me move to this. So in general, computational methodologies, CFD methodologies, the very typical way, if you do research, you hear more or less, it is what we call continuum fluid dynamics. So you have the set of second order partial differential equation PDEs. Then based on the conservation laws, right? If you take the fluid mechanics class, we know how to derive those equations, right? Then using different kind of schemes, finite volume, finite difference, finite element. So you discretize the set of equations, then you do the kind of the computation, then you resolve the system. That's the general process for CFD. But we are on this lattice Boltzmann, it's kind of black here. We're on the mesoscopic level. So on mesoscopic level, actually your start point is not the continuum equation. It's kind of the discrete model already. So in that case, we usually call it digital fluid dynamics, not the continuum fluid dynamics. Okay, but these equations are based on the same conservation laws plus some kind of symmetry needs to derive this equation. Okay, then you do the general computation, then you achieve the same physics you would achieve from CFD within the flow regime, right? So, but I mean, so we're all familiar with this derivation. Basically, lattice Boltzmann method, the equation will recover the Navier-Stokes equation within some limitation. I mean, the flow regime. Okay. So in that case, for a flow system, the physics will be unique, right? The flow system itself does not know you are using the general CFD or you are using the lattice Boltzmann mesoscopic level simulation, right? So we expect the outcome should be same in some kind of accuracy, accuracy orders. Okay, so that's kind of the pretty much the general introduction of the CFD. So we are here. Okay, today I'm not going to go to the details. I promise you, because you might care about the details. We care about details. You just learn about the big picture, about what we are doing, how we are making contribution to the research fields. Okay, so now come to this image-based CFD. Image-based CFD, I think that the first motivation is to simulate blood flow in human circulation systems. So it's kind of a more realistic applications, right? So you are really doing blood flow in human arteries or vessels, something like that. But it has the engineering application as well. This is also petroleum engineering, which I collaborated with a professor in China. We did that. So basically, they were doing porous media flow, but the porous media structure was imaged by micro-CT machine. We have a very big micro-CT machine. So we take that image over, then we quantify, we simulate the flow in porous media. But the prevalent approach for this type of image-based CFD, actually you can see there are several drawbacks. First, you need to go through different software. For example, in this case, when after you get the medical images, like CT, MRI, you all know that, right? You may not see them, but you know people when they go to hospital, then if you have some kind of artery problem, then doctor will order you to do CT imaging or something like that. So after we got this, we need to, because of the CT image, for example, you do a CT for carotid artery, but inside this area, there are many different arteries and vessels, and also bone, a lot of information. So the first thing, you want to what we call 3D reconstruction or image segmentation. We want to identify the specific disease artery from the image. So that is the first technique we need to do. Then eventually we will use the CFD software, for example, ANSYS Fluent or like OpenForm. There are very famous this kind of a packaging. But because this software, they are not necessarily connected to each other. So to make a connection between this disease artery system to the kind of the CFD solver, you need to go through additional software to make the connection. So if you do this, then eventually you will have find out the hydrodynamic abnormalities to provide insights to the vascular surgeons. Then they can decide if this disease needs to be treated immediately or it's mild. Then they can wait like for 6 months follow-up or something like that. But if you go through this process, it's kind of there are several drawbacks there. And also, I think the biggest problem is the limited capacity of high-performance computation. Because doctors, once a patient got disease, have some pain, or even heart attack, some kind of a disease, you would not want to ask the doctor, wait for me for 2 weeks, I will do the simulation for you, right? Usually they can maybe wait for 1 day or some that kind of. So we really want to do the high performance, the computation, okay? So that is kind of what, in the world, many groups are doing. This is not very new. This is not very challenging. People are doing because you just need to utilize the software. So many groups are doing. So my group actually developed, we spent 13 years so far, since 2012. We developed a computation package. It is so based on the imaging information. We actually extended to engineering application as well. So engineering application, we usually use CAD design, but we can save it as an image. So in that case, we can use this unified package to do engineering application as well. But at the very beginning, so from the medical side, we have this integrated package, which does image. The next slide I will show the image processing and the CFD with a seamless connection. So in that case, you do not need to go to additional software to make the connection between the geometry of the artery from the image segmentation and the CFD part. And after that, then after we got the raw for the CFD data, then we can do a lot of analysis, right? To what we call post-processing. So using, the TeraView, Python, MATLAB, Python, different software to visualize the flow abnormalities. Right? This is a very necessary step. Without that, you tell the doctor, we have this data. We have number 1, 2, 3, 4, 5. Then the doctor does not know what you are talking about, right? We must show, okay, there is a swirl here, there is a big wall shear dress, so we must show. So that is called the post-processing, which is a very necessary step in this package. So we actually use that for both. this is very innovative, but it's an old. It's not very new, but this is kind of a novel way to solve that. To do the image segmentation using lattice Boltzmann. We have the publication. It was many years ago already. So this is the image segmentation. The output of the image segmentation is the input of the CFD part. And the CFD part, we use also lattice Boltzmann method. So in that case, these two are seamless connected, right? Then we put the entire package on GPU parallel computing, okay? Because today I not introduce that. The truth is, lattice Boltzmann method is ideal for GPU parallel computing, okay, which can be very fast, okay, high performance, okay. So this is our package. We have some kind of a GPU performance assessment, but it was like around 2015, very old, because we published several papers. Then after that, we know GPU accelerates a lot, so we didn't do that kind of assessment anymore. But even with that, and the kind of the old hardwares, you can still see. So if you look at here, parallel versus not parallel. It can speed up, for example, for this image-based blood flow in human aorta. So if you do not do the parallel computing, for this case, the largest resolution side, it takes 26.4 hours to do a run of simulation. But with the GPU acceleration, it drops to 0.14. So the speed up is kind of a 129, but really it is 194. So really based on the geometry, based on the equations you are solving, so the acceleration may vary, okay? But in that case, it's still. Now, in terms of CFD, there is kind of an advancement of CFD capability. So originally, or very kind of an initial stage, for example, industry, I'm giving an example in industry. So people, like engineers, run CFD simulations to optimize the aerodynamics of a new electrical SUV during its design phase. So in that phase, actually, they just have some kind of a assumed or hypothetical wind condition, and they have like a CAD design shape, usually a box or something like that, not the real kind of SUV shape. In that case, they get some kind of insight about the flow surrounding the SUV, how kind of the shape or the kind of the drag force, all those. So in that case, their simulation results do not have direct impact on that specific SUV. It's just a general insights, okay? The second step, it is kind of on the monitoring stage. So in this stage, they have the physical object. So then they will use that physical object, the geometry, the shape, to do the simulation. So it's kind of one step close the real world, right? But actually, after they got the simulation results, they do not go back to that physical object. So they just gain some insights and to monitor this stage. So this is the second one. So very recently, people started to develop this kind of a two-way simulation. So basically, the digital object, the computation platform, is based on the physical object. So we want to use exactly the same kind of the physical conditions, the geometry, the flow conditions, the pressure of atmospheric. So everything is based on that digital, the physical object. Then you develop the computation platform to simulate the flow for that specific flow. And after that, these results will feed back to provide any kind of control, optimization, that kind of insights. Okay, so these are kind of the three types of CFD. And you can see, so this one basically we call digital model. No any specific communication between the physical object and the digital object. The second one is called digital shadow. So the digital object is developed from the real one, but after that it does not go back to that. So in that case, they can expand their applications, right? But digital twin, actually, it must have the two-way or the mutual communication, meaning this digital object is specifically developed for that physical object. Okay, so in that case, so this is very new. It's let me point out this very new review paper 2025 talking about this kind of digital twin technology. So basically, you have the physical object, you have the digital twin. Okay, the digital twin is developed based on the physical object through the simulation, but it will be back. So really, the concept of the digital twin will be real-time mirror. So no twin, right? If you have a twin, these like stand next to each other, then you can recognize they are not identical, close to identical, right? Something like that. So it's twin. Twin is a real-time mirror and a smart tester. Because we use computation, then the cost will be much lower, and the environment, for example, sometimes you need to simulate the explosion, and it's very, you have the safety concern, right, to the experiment. But if we do the digital twin, we use the computation, then no that kind of safety issue. And also it is a helpful partner. So this is the concept of digital twin. Okay. Now let me give you an example. We have been already. How many?
No. Half an hour.
Okay. Yeah, I need to move faster. So let me give you an example about this digital twin for human arterial stenosis. So this is the physical system. You can see there's a stenosis. Stenosis is an abnormal reduction of artery. Okay, later I will show you. It can occur all these major arteries. So this is so we actually have built up the digital twin for specifically this part. Okay, so to build up the digital twin, we actually use the clinical for that specific patient. So this digital twin is for an individual patient. Okay, then we use the clinical imaging data, for example, CT or Doppler ultrasound. That doctor orders all those imaging for that patient. And usually they do lab tests as well. That's the very first step. So we use this information. We use advanced modeling and the computation techniques. Okay. Also, we include the systematic uncertainty computations because in that process, a lot of uncertainties are involved. So, we have built up a team with multiple expertise in this all these aspects. So after that, we can provide complete 4D hemodynamics. 4D means 3D in space, 1D in time, because the blood flow is pulsatile, right? It's always varying with time. Basically, we have velocity, pressure, wall shears, all this information from the computation. Then, in that case, we can provide the feedback to the specific patient. Okay, so for example, non-invasive prediction about the pressure. Before and after the pressure drop, before and after the stenosis, something like that. So, eventually in the big scope, basically we want to have actionable clinical insights. Later I will show you, we are developing a new hemodynamics for like a specific stenosis. So once we get the patient's data, the imaging data, then we will tell the doctor if this stenosis is severe. If it's severe, then we recommend the doctor to do the stenting. Stenting is a surgery to open that, the narrow down artery, that area. But if we identify it as a mild, then no need to do any kind of a surgery, something like that. So we have a pending NSF proposal for this technique. Okay, let me very briefly talk about the physical system. So arterial stenosis, you can get, basically it's just a reduction of that. For senior people, it's very common. Okay, you are, majority, you are very young, so you talk to your grandma, grandpa, then they will care about that. Okay, but it's very common. For senior people, it can occur coronary artery, the leg artery, like iliac or femoral, and also carotid and cerebral, renal, iliac. All these big arteries will have that kind of a abnormal reduction because of the atherosclerosis. And when you are aged, it's very natural to develop buildup inside the arterial wall, right? So I'm going to skip all this information you can see. So in medical practice, actually it's quite easy to identify the stenosis using CT, MRI, or X-ray, ultrasound, all those kind of imaging modalities. It's very easy to identify somewhere you have the reduction of the artery. So basically a stenosis there. On the other side, if the doctors know this is severe, so it's a matured surgical technique as well. So they can do revascularization. So in this case, you see there is a stenosis here. After surgery, they insert a stent to open it. Then after that, it becomes normal. So that's the, but in between, actually, there is something missing. Okay, for doctors, how to know if stenosis needs to do the surgery. It is not necessary that you just waste your money, and also you have the risk to have the complications from the surgery, right? But if it's severe, you do not do that, then you then get heart attack, something like that. Okay, so actually in medical practice, they all know the pressure drop before and after is the main indicator if the stenosis is severe or not. Okay, so I'm going to skip all those details here. Let me just provide you some kind of a clinical practice limitation. In clinical practice, to identify the pressure before and after the stenosis, it must do what they call catheterization. So they use a very long catheter, and starting from lab. So if it's here, then it's a very long journey to reach here. Then they use the pressure transducer to measure the pressure. And if it is a coronary artery, then again, so sometimes they put the catheter through the arm. So in any case, it's invasive. Invasive really means very high cost. Okay, for example, in U.S., the hospital I am affiliated with, in my campus, to measure the pressure before and after the stenosis in coronary arteries, it costs $4,400 US. That's the cost. And there is a big risk because when the catheter going through a long journey, it's very easy to hit the wall, to damage the wall. So some kind of so that because of that, so in medical practice, doctors are more diagnosed the severity of stenosis based on the CT measurement. So the CT measurement is really, how much the lumen reduction is, right? Which everyone knows is not accurate at all. So we are in a so like I said, I do not have medical biology that have background. But we are in a very good position. I'm from mechanical engineering right now. I have the background in physics and aerospace engineering, and I'm doing biomedical research. So basically, we can, once the patient's images, information are provided, we can use the CFD methodology to non-invasively quantify the blood pressure before and after the stenosis. Okay, so that is what we have developed. So I have the platform is called Vascular. So once you have that imaging information, we can quantify the 4D flow hemodynamics in the disease artery. Actually, this package is also works for coronary, for capillaries. Capillaries is like a pulse media, right? So once we have the image, but to us, for the vascular, it's the same treatment because everything is automatic. Once we have the image, then we cannot do the image segmentation using the same method. Okay, so in that case, I currently have another project to do, again, it's kind of a senior common disease, it's called AMP. So it's kind of the eye, the blind, that one. Okay, so let me move fast. Because when we do this kind of simulation, the validation data is very limited. Because like I said, the doctors do not want to do the invasive measurement, right? So in that case, we actually we spent maybe 5 years so far. We build up what we call mock vascular circulation loop. So in that case, we do 3D. So this is a doctor I worked with for many years, my friend already. So we have this test section. We do the image segmentation. We use a 3D printer to print out the disease artery. Then we mount it into this loop. Then we can measure pressure. So it's kind of similar to the computation, right? So we can kind of do the validation from both sides. Okay, so this how many minutes I have?
You have spent like 40 minutes now.
Okay, how many more?
10.
Okay. So in that case, this is a very busy slide here, but that's kind of the core. That's kind of I spent maybe 12 years already. I mean to do that. So the starting point. So we are developing new hemodynamic index to determine if the stenosis is severe or not. Then provide recommendations to the doctor, the surgeons. Okay. So if you follow me from A, B, C, D, then you pretty much you can get the points, okay, what we are doing. So starting from those imaging data, we use Vascular to quantify the pressure change. So PA/PD are two pressure values before and after the stenosis. So there are two, in medical practice, there are two ways to determine that the pressure drop. Either use the subtraction or use the ratio. I mean, for different arteries, I'm going to skip that one. Then, yeah, we have 2019, this package is called the non-invasive quantification of pressure. We already got the U.S. patent in 2019, but that is not enough. Even you know that the pressure drops for coronary, because they have the gold standards. So for coronary, if you know this FFR, then basically doctors will know if the stenosis need to be treated or not. But for other non-coronary stenosis, no gold standard. So doctors, even after they know the pressure drops before and after stenosis, they still don't know if it's severe or not. So further this, the first patent, so we actually invented a engineering methodology to address this one. So basically, we manually, so you have the stenosis, the solid line, right? It's around 60%. So we manually vary the stenosis degree. Then each degree, we quantify the pressure drop. Then we can have this curve, right? So this curve, once you can see from the slope, so this side is kind of a flat, this side is kind of a steep. So basically, we identify two thresholds. One is called mild, another is called severe. So then the last one, that's the new hemodynamic index. Based on these two thresholds, you have the existing stenosis, right? Then you just compare the mild side, the severe side. You can determine if I'll give you examples later. So basically, that is how we determine if the stenosis is severe or mild. Okay. Yeah, so we actually got another U.S. patent. We have the third one pending. So this one is also pending NIH. Okay, so let me quickly show you how accurate we can achieve for the non-invasive pressure computation using CFD. So the doctor I work with, he provided us certain cases with invasive measurement. So in that case, we can do the validation. You can see non-invasive means computation, invasive means pressure, the catheter measurement. You can see we achieved, so this is for the same case before surgery and after surgery, for the same patient. You can see we achieved very good agreement between non-invasive and invasive. This is one example how we define. So once it has this RAS, so we use the methodology to establish this curve between the pressure drop versus the stenosis degree. Then we use the existing stenosis to kind of locate the location on this curve. Then we determine. So basically for this one, it is, so this is the severe threshold, this is the mild threshold. The existing one is out of severe. That means the stenosis is severe. Okay, and that's our prediction. Then comparing with the medical practice, actually the doctor did the surgery. So that means we have agreement with the so this another example is we go through the same process using the experiment. So it is for iliac triangular skill. So 2 cases here. Okay, so the challenges to build up digital twin for artery stenosis, I do not have time to read through, but there are physiological, biological challenges, technical challenges, clinical and translational challenges. But it is significant if you can develop it, right? So in that case, we provide the engineering insights. We are engineers, so we're not doctors, so we're not those expertise. So we provide the engineer sites, we do simulation driven innovation, and definitely we impact healthcare, right? And also, like my student, when after they graduate, it's very easy to find a job because it's very hot right now. There are many startups or big companies related to this. Okay, so next part, it is related to the work here. Like I said, it's under construction, so I do not have much to say today, but just some idea. So I'm learning these days. I'm learning from different talks in this group. So once I understand the physical system, then I intend to build up the digital twin for that specific system. It's called the subsea spill mechanical. What's happening here? Okay. I stole these pictures from one of the students' slide. Okay. So basically the idea is, like I said, if you are building up a digital twin, the digital twin should mimic, it is a mirror, right? Mimic the experiment. Okay, so we will use all this information from the physical system. We build up this computation platform. After that, then we will provide kind of feedback to that system. But I think that eventually we want to do kind of more general. We want to, the first step, we just do the digital twin for the experiment in Dr. Nebo's lab, right? I talked to Dr. Nebo a lot about this one. So, but in the future, I think more meaningful, more practical, we want to be able to develop a digital twin for the real scale, like in ocean. But it will be extremely challenging because of the computation limitation. Okay, because the real size, okay, so in any case, so I also put some challenges here. Also, if we can make it, it's significant. It's the same thing, right? So, but I'm just a jump. I want to just jump to the take-home message. It's okay. But for that part, so wait maybe next year when I come again. Hopefully we have a very meaningful results. Then I will talk about details to you, okay? Take home message. First, what is a digital twin? Okay, it is a real-time sync of physical and the virtual systems. They are twins, okay? And they should have a mutual communication. If single communication, it's called a digital shadow, not digital twin. Second, the key development fuse real-time data with the high fidelity models for live decision support. Okay. Then frontier research, like I said, this one is very hot. It's very new, even worldwide. Okay. But I actually, after I learned about this term, I just realized that actually I have been doing that medical projects because I was developing the digital twin, basically. So that's kind of a new thing. So I jumped in very naturally and quickly. And of course, any application will have challenges and a major significance. So it's always like a no pain, no gain, right? And also, I have this. This is an English idiom, but we have the Chinese idiom as well. It's called "where there's a will, there's a way." It's in Chinese, it's 有志者事竟成. If you work hard, if you believe you can make it, you make it. That's what it is. Thank you so much. That's
for this very inspiring lecture, and we have time for questions. Please.
Yes. Good morning. Do you have a microphone?
My name is Luiz.
Production.
And I would like to ask, my question is applied to the oil and gas industry. My question is, nowadays, is it feasible to implement real-time digital twins in a complete system, or the hardware limitations, so high computational tools is still a large-scale, still present a large-scale adoption?
Yeah, very good question. I think Luis should answer much better than me, but let me try because it's my senior right now, right? So I would say digital twin, that's our goal. We are still presenting, but we're still kind of developing. But to do the CFD, solving Navier-Stokes equation and the related equations, in that way, it's not feasible because of the computation cost. But there are different ways to use like software. For example, Luis students are using All-Star. So in that case, they are not solving the details about the flow, the velocity field, the pressure field, but they can get the insight for the specific quantities, interested in that project. So the answer is yes, but I would say very hard. Okay, thank you.
Okay, thank you. We still have time for questions.
Do you have any questions for us, for your grandpa? Because I always got this. With me, my uncle just recently got a heart attack because of the stenosis also. Then I said, oh, I'm not a doctor. If you provide me the image, I may do some analysis, but I'm not a doctor. I cannot provide any information related to the clinical. Yeah. Yes?
For the wonderful lecture.
Thank you.
So I have a couple of questions about this cardiovascular
Yes.
study. So the first question could be, so what kind of inputs given to the CFD from the doctor?
Oh, okay. So yeah, to answer, very good question. I actually skipped. I didn't say. I was saying we use Latin Postman method, but basically I invented the paper published in 2014 in PRE. I invented. It's called volumetric lattice method. So basically, the grid particles are not sitting on the nodes because you are doing this, right? If they are sitting on the nodes, then once you have curvature the boundary, then you have to do the interpolation to identify the kind of the portion of that group. But if you do volumetric lattice Boltzmann method, so we are considering the lattices with the particle population, not the distribution function. So So in that case, at the very beginning, it's kind of the end of the image processing. We will calculate what we call p-value. P-value is the solid, the mass of solid versus the entire mass in that lattice. So in that case, if it's a fluid cell, then p equal to 0. It's a solid cell, p equal to 1. But if a boundary cell, p varies from 0 to 1, right? So we actually embed that p-value in all the lattice Boltzmann equations. So once you deal with the image segmentation, you forget everything. You do not need to deal with the bounce back, everything. It's already clear. You will love it if you want to try. Okay. Yeah.
So that's a geometrical input they give you. So how would the flow input, for example, the velocity field or flow rate?
Oh, that's the same thing. You just see. So you have the inlet exit. You just at the inlet, you just provide the velocity profile there. So the velocity profile is from that patient's ultrasound. They have the wave. Yeah. So we use that. Yeah. More questions?
Last question about the hemodynamic index that you mentioned.
Yeah.
Give the strength of the canopy.
Give the what? Yeah.
I understood that is purely based on the pressure laws.
Yeah.
Does it related to wall shear stress in some form?
Related to what?
Wall shear stress.
What should, oh, yeah, very good question. So for stenosis, basically the pressure drop indicates the severe. But for aneurysm, it's kind of a abnormally enlargement of the artery. That disease, it is from the wall-shear stress. Yeah. But in our simulation, because we calculate the pressure wall-shear, so they are already there. So whatever doctors they want, we can just do the post-processing. Yeah. Very good question.
Yeah, we still have question. We still have time for one or two questions. Ou seja, tempo para uma ou duas perguntas. Se você quiser fazer em português, também pode, tá? Fica à vontade. Tem vários tradutores aí. Ou pode fazer em inglês também. Treinar o seu inglês.
Yeah.
Ask you, how you discover about this area to research? Because it is obvious area to work with engineering, medicine. And why you started to work with it? Having so much people choose any other area to work.
Okay, very good. Okay, so like I said, actually I did 2 PhDs, 2 postdocs before I became a faculty member in that university. So before that, I never touched any, I have 0 level of I even didn't know how the heart is beating. So, but after I joined that campus, previous I applied, it is a life science campus. The Indiana State, the biggest, not the biggest, the only medical school is in that location, in that campus. We have at least 5 very big hospitals there. So in that case, at that time, I need to decide which direction I go, because I have PhD supervisors, postdoc supervisors, they are competing with me, right? If I continue to do whatever I follow them, then I must compete with them for the grants. So I really wanted to start a new direction. And also, I have the expertise on the Boltzmann method. But my PhD supervisors, the postdoc supervisors, they do not have that expertise. So then I know we can non-invasively quantify the blood flow in real human bodies, right? So I really wanted to change the gear to a new direction. And because doctors, actually the doctor I work with, he has an electrical engineering background in undergraduate and master. So he actually approached me saying their kind of needs. So that's the reason all my research, actually it is the need-based. So we're addressing the clinical problems, not for fundamental study. those BME research scientists, they are doing all those fundamental things, but I'm not capable. I can just address using the engineer method. We're engineers, right? We can do everything as long as you have the need, right? Maybe it's just a simplified, but we can always do more or less. So that's how, did that answer your question? Yeah. Okay, thank you.
Thanks, Nora, for the very nice question. We have time for one more question. The last one. No, not today. Next year, then? Okay. So let's thank Professor Whitney again.
Thank you. Thank you.
Obrigado.
Thank you. Obrigado.
Yeah. So let's stop sharing.
Hi, I'm good, thank you. Uh-huh.